Welcome back to a video. Today exploring Ethernet lower layers. What does it mean? We will check the electrical signals on an Ethernet cable to check what's going on and also explore how do we get the bits out of it. As always, the link to this website you find in the description of the video. So blah blah, it will be explained what standards are there. Today we are looking at IEEE.3.I, which was released in 1990, quite a time, and it's 10 megabits, so nowadays 1 gigabit is at least the standard. You find descriptions here. How does the setup look? We will use an USB Ethernet adapter from Ugreen capable of 10, 100 and 1000 megabits per second. We will set it to 10 megabits per second. We will have a check on the datasheet and how do we extract the signal from this USB adapter. We will use an USB oscilloscope from Digilent. It's called Analog Discovery 2. It's quite a cool device. It allows 2 scopes and acquire 2 signals at the same time with up to 30 megahertz bandwidth. If you're interested in such a device, it's already legacy. There's a newer version available, but you can find the link here to check out the details. And the setup, we will use the USB oscilloscope. We will use the PCB and put the probes on the signal and check what's going on the line. A quick check to the setup. We will have 2 PCs connected. One is PC1, is a test dev PC with IP and MAC address details. We have a PC2, which is actually my PC where I also record the video. We have the USB to Ethernet adapter where we put the probes, which via USB is controlled via this PC. And to go into details, here showing the internal or basic components of the USB Ethernet adapter. We connected to my PC via USB. On the board, we will see that later in the video, we have the chipset. This is actually from AX Lite. And we have an EEPROM containing, let's say, MAC addresses, which should be unique, and serial number, and etc. We have the magnetics. This is always there. There's a little transformer before it goes to the RJ45. And we will put the 2 oscilloscopes probes on the TX differential pair. Okay, let's start doing. So here you can see I have an Ethernet to USB or USB to Ethernet adapter. And today we are going to open this one and we will scope on the physical layer what signals are going to be sent if I just send network traffic. Before I can do this, I have to somehow open it, and I think we need to use raw power here because I have no clue how it opens. But I assume, okay, if I play a little bit around here, that it will go out in this direction. So let's try this. Ooh. It's already broken. Alright, good. So as expected, it opened smoothly. Unfortunately, I destroyed the housing, but anyway, this is I think €10 adapter. Okay, and this is how it looks inside. So we will have a closer look when I have my microscope out. There are some components on this small form factor. Just some information to this adapter. This adapter supports 10, 100 and 1000 megabits per second on different standards. We will have a look later on this. Yes, and I used it already, but I have now a new one with the USB-C connection, and this one we will use for fun and evaluation. Good. Then let me get out the microscope and see you in a minute. So let's have a closer look on the PCB first. All right, good. So what are we going to see here? We see, okay, here's the RJ45 connector. Here's the transformer for it. These are actually quite large parts here on the PCB. We have a microchip where we'll have a closer look in the datasheet later. We have a clock source here, 25 megahertz. It's very common for Ethernet applications. Because you can mix the frequencies you need for the physical layer. We have some conductors, resistors, and other ICs. And here we have the USB connection. This is actually USB 3.x. Yes, and it is used for high-speed connection. Okay, what do we have on the rear? On the rear side, we also have some connections. We have resistors and conductors again. Here is one chip. Don't know what this is. Could be some kind of an EEPROM or something like this. And a lot of resistors and conductors. And we have another half of the USB connection. Genau, that's it. Let's see if we have a closer look here. You already see, okay. It looks like that here there are already differential pairs going away. So looks a little bit like, but we will have a closer look what this means. That here we have a differential TX pair, here a TX pair maybe, here an RX pair, and here an RX pair. But we will see what this is later. Same here. On this side, after the transformer, you also see, okay, we have different connections here, which are done on the back, and these are our Ethernet connections. So let's have a closer look what is going to be. Okay, so I just got out the datasheet of this chip here, which we explored on the board. And this is actually a single chip USB 3.0 to Ethernet 10, 100, 1000 megabits. And there are some cool features described here, but this is not of care of us. Our next task is for the oscilloscope to find out on which on these lines there's the TX and the RX, the transmit and the receive paths. So let's scroll a little bit down here. Here, by the way, is a nice block diagram, so how such a IC looks from inside. And here we can already see, okay, the gigabit Ethernet PHY is connected to the MDIP and MDIN, so this is differential, and there are apparently 4 pairs. So let's check this here on the pinning. Okay, we already see them here. MDIP, MDRN 1, 2, 3, and where is the 4th one? 0, 1, 2, 3. Yeah, these are the 4 pairs. Okay, then let's have a look on which standard which pair is going to be used, because for the moment we will check the 10 megabits Ethernet, so the 10 base T. And if we look here, okay, we have the MDIP already, and for 1000 base T, this is actually the jump pair. And for transmit, for the 10 base T, which is of interest for us, and also for the 100 base TX, which we will evaluate in another video, this is the transmit pair. So MDIX 0 is the transmit pair. So, and then let's have a look. Okay, the second pair is for 10 base T something else, and here for 10 and 100, it is the receive pair. So If we go to the pinning again, so we see, okay, the 0 is the very on the top, and 1 is them above. So in the on my PCB, I can see this already here. That means this is actually the TX and this is the RX line. So we have to go, we go with our oscilloscope to these differential pairs here. We will see, we will test one after the other. All right. Okay, then I have my picoscope here. And I would say we just position our needles right here. Okay, I just connected another microscope here that you can see that how it is connected. I hope they're connected properly. Yeah, and let's see what's going on the scope line. Okay, here you can see once again the setup. We have the USB scope with the 2 channels connected to those 2 probes, which are connected to the TX pair directly here on the PCB board before the magnetic, but after the chipset. Here we have the ground connected of each probe, and we have an Ethernet cable which goes to the opponent PC. So quickly to the terminal of the 2 PCs. This is PC1, this is PC2. Let's have a quick look on the interface. This is there are details like the IP address, like the MAC address. This is actually the PC where the USB adapter is connected. This is the reason why it has such a complicated interface name. And this is the PC on the other endpoint. Also has an IP address which only is different. Here we have 10, here we have 20. And also has the MAC address. This will be important for later use. So before we go to the scope, let me send IP packets from my PC. I wrote a little one-line loop, which is endless and uses netcut to send the in-hex dead beef. I'm using netcut to send this to this IP address via UDP, and it does it every half a second. Let me start this and then change to the oscilloscope. Here we can see the software of the oscilloscope. We have many measurement devices, not only the oscilloscope available. We have a waveform generator, for instance, spectrum analyzer, and so on and so on and so on. Okay, let's change to the scope settings. Here we on the right side we have channel 1 and channel 2. Let me change the color to green, as it's also green on the marking of the probe. And also let me, because the scaling is 1 to 10, so for both channels, let me change this. All right. Then the trigger, the trigger is currently the source by channel 1. We will have both of those triggers, and let's see if we see already something. So here you can see we see already something. Let's trigger again. And here we see a signal. So what are we seeing here? Yeah, we see a signal which has basically 2 levels. One is roughly about 3/4 volt, and the other one is minus 3/4 volt. So these two levels are exchanging. We see that the signal has a certain pattern here, and here it becomes more random. We can also enable channel 2, which is the probe of the other differential signal, and we see, okay, this is the exact opposite of the signal. So this is actually what a differential signal does. What we can do here on the scope is we can add a channel, here a simple mask channel, and we have the probe C1 and C2, and we'll just subtract from them from each other, and then you can see the red signal, and this is what actually basically the differential signal does. So on the receiver side it subtracts those two, so channel 1, channel 2, and then the receiver gets the red signal. And the purpose is like this: if you have, let's say, an impulse distortion or impulse impact on the cable, let's say the cable goes close to a Hoover or electrical engine or whatever, and the signal is impacted by the electromagnetic impulse, then always both differential signals are impacted, and the differential result will still be the same. I will disable the differential signal now and also channel 2 as we have seen it, but we can stick to channel 2. Okay, let's have a closer look to the signal. Yeah, we see here it's quite a long signal. And yeah, to now make sure it's a signal of interest, we will zoom in. And we should measure its symbol rate to see if this is the signal of interest. In order to do this, we will check for the smallest symbol transition, and we have found it here. And we will use this tool to measure it. So we have a symbol here and a symbol here. And we see this is roughly 10 megahertz, in this case, and 9901 nanoseconds. I hope you can see it here on the display. So looks like this is the signal of interest. Okay, so I will stop this again now. Okay, what can we do with the signal? So somehow we have to extract the bits out of the signal. And normally you could think, okay, this lower level could be a logical 0 and the upper level could be logical 1. But in this case, it's not as easy, as there's a line code on the signal, a so-called Manchester line code. We will check the details now. Okay, if we go back to the browser and scroll a little bit down, here's actually what we just have seen on the scope. And here we have the details to the Manchester line code. Let's ignore the clock for the moment. You can see we have here a data signal and two Manchester signals. We go with the Manchester signal as per IEEE 802.3. And you can see, okay, we have we have the first logical bit, which is 1. And this means in Manchester line coding, we start with a low level signal and it goes to an upper level, and that's representing the logical 1. If we go with the next symbol, we have a logical 0. So the higher level, or the symbol goes from a higher level to a lower voltage level, and so on. So in Manchester, that means in each logical bit, we have always a transition within the signal. Which gives actually one advantage. You have a clock recovery and you have a quasi DC-free channel. This is important for the channel characteristics. In most cases, you don't want to have a DC offset on your signal. Also keep in mind, if we have consecutive logical bits, as we see here, we have two logical zeros. Then if we go again, Logical 0 means from lower level to higher level. And then it goes directly down in order to represent again the 0. So there can be also transitions within two symbols. And this is actually what we basically see here on the scope. At the beginning, we see, okay, we have an alternating bit sequence, as we see here on the first two, on the first 3 or 4 bits. So, and if we go further the line, you see here symbols closer to each other, so that means there are transitions between the symbols. Okay, if we go with the explanation, keep in mind, if we look back to the browser, we have for logical 1, we just need to remember low level to high level, logical 0, high level to low level. Okay, if we keep this in mind and we go back to the scope, then we see, okay, lower level to a higher level. So this would mean here we have a logical 1. Then we have, because this is half a symbol, so this transition is really the next symbol. So we have level up to level down. This is a logical 0. We have level down to level up. This is logical 1. So it looks like this sequence here is 1 0 1 0 1 0 1 0 and so on and so on and so on. And here it's getting more complicated. What we can do here, the software allows to transform these bits into logical bits. We just click here on digital. I selected the scope channel 1. Here you can set, okay, what one do you want as hysteresis? Let's take 0 volts. And here, maybe 200 millivolt as it's set already. This should be fine. And we can see here already, okay, this is a 0, this is a 1, this is a 0, and so on. And we can also add here a Manchester decoder. And what we set here is actually, let's call it Manchester. It's on scope channel 1. It's actually the rising one. So this defines the two. If we go back to the browser, it defines the Manchester according to IEEE or via G.I. Thomas. Then our rate is 10 megahertz. We have 8 bits, LSB, and we have a preamble. We will have a closer look there later, but we will leave it to 0. And yes, let's add this channel here. And you can see here from, if we do the exercise again, in the browser, if we remember, from lower level to higher levels, this is logical 1, and from higher level to lower level, this is a logical 0. So you see we have an alternating, maybe we can disable this here, as we don't need this anymore. Remove this one. So we have an alternating sequence of bits. And in hex, this is also here. This is hex 55. Okay, here we see our signal. We see the extracted logical bits down here. And now let's have a closer look what this actually means. We see, hey, there's a long frame that somehow ends at the end. Okay.